Okay, good morning everyone, welcome back. So today we are going to finish chapter 4 and go to chapter 5. So chapter 4 was about participating in electricity market, and we discussed several points: the consumer's point, producer's point, and what? Retailer's point, blah blah blah. And the last topic is, so now I think you are familiar with the contents of chapter 4 because you did your homework. Okay, so we are perfect competition, imperfect competition, and then chrono competition, Butland model, scheduling of storage. Yeah, we are here, right? So let's talk about overall market perspective. So as you see, the market determines the market clearing price, and that is the intersection of the supply curve and the demand curve. So yeah, this is offer curve. The x-axis is the offer generation capacity, and y-axis is the offered price. So recall yourself, at this price, how much the producers want to generate, and the collection of that is an offer curve. And interestingly, we have this kind of things. That means, even though you give nothing, they still want to generate. That is because shutting down the power plant incurs additional cost. So as long as the penalty is less than the shutting down and rebooting cost, then they still can offer. Okay. Sorry, as long as the penalty is more than my shutting down and reopening cost. And also, we know that the demand changes over time. So this is time and this is the load. So it changes over time. During a day, we see the minimum load, we see the peak load. And typically, we see this kind of small drop around 12 noon because at that time, people need to eat lunch and they do not work. Then, anyway, the demand changes over time. But anyway, for the given price, we can think of the total demand. And this is for hour 3 and this is for hour 11. So, obviously, as you see here, the demand changes over time. So we have different demand curve for different time. Okay. So anyway, the intersection of this demand curve and this supply curve determines market clearing price. So this offer curve is fixed, but demand curve changes over time. So this market clearing price changes. So that's why the SMP, system marginal pricing, changes over time. And this is an interesting figure. This is called price duration curve. And price duration curve of an ISO, so independent system operator. And the interpretation of this curve is that, again, this is price and this is the percentage of hours. So you can think this is something like cumulative distribution function. But this is the x-axis and this is the y-axis, and this is kind of complementary CDF. So the interpretation of this curve is that, for, how can I say? So for 10% of time, the market clearing price is at least $90. Okay. So for 20% of time, the market clearing price is at least $60 or more. Okay. Or you can interpret this: the market clearing price is $100 or more for 80% of time. So this is price duration curve, and different ISOs have different price duration curve. So this is the example of ISO NE, and this is the example of AESO, that is the Alberta Electric System Operator. So Canada, Alberta is a state of Canada. And yeah, very, very different price duration curve. This versus that. Anyway, this is the average price. No, because this is kind of distribution, we can compute the average price. That's this one. So when you look at this, for very small portion of time, this is the average price, but the price can be very high. Right? You see that. Similarly, in this AESO price duration curve, this is the average 2050 average, 2015 average pool price. How much? $30, $40. But sometimes the price is almost $1,000. So more than 20 times higher than the average price. So this kind of price fluctuation happens because of the shape of this offer curve and the change of demand curve. And whether the intersection happens at this point or that point or that point, if the demand changes around this time, the market clearing price does not change much. But if this demand curve changes here, you see intersection here or there. So this is a very sharp. Okay, that means in this range, the producers need to use very expensive generators. Okay, so that is called the price fluctuation is called price spike, because literally we can observe the price spike. So price spikes because of the increased demand. Given offer curve, this is a normal demand curve, but if that is shifted to the right side slightly, this price goes up. Okay. So small increase in peak demand cause large changes in peak prices. And this is the example, price volatility in the balancing mechanism. So this red line is the average SBP system buy price, but you see a lot of fluctuation. The blue line, 100, so like 50 or something like that, but 10 times higher than, sometimes almost 20 times higher than that. So when you look at this, you may want to take this opportunity. If you have a storage, you can buy energy when the price is low and sell the energy when the price is high. That is called arbitrage, right? So we can do the energy arbitrage in wholesale market using energy storage system, or we want to do the similar thing using home energy storage system, right? Anyway, the price changes over time. So when the price is low, charging the battery. When the price is high, discharging the battery. But you also need to think about, even though this price fluctuation is that high, it's not easy to make money. First, you need to predict this kind of price fluctuation. And also, even though the price peak is that high, your revenue is the product of price times volume. And typically the volume is not that much. Okay? So it's not quite easy to make money using this price fluctuation. But anyway, demand response or energy storage system, those things are the one to mitigate these price fluctuations. Then let's talk about market power. A firm exercises market power when it reduces its output. So what does that mean? This is our supply curve, and this is the given demand curve. But if you can shift your offer curve slightly to the left-hand side, you see the intersection changes from here to there, right? So by withholding your generation capacity, and if you are a dominant player in the market, you can exercise your market power and manipulate the system price, right? So that's why the regulator need to prevent the generators from exercising their market power. So that is called physical withholding. Even though you have enough capacity, you do not generate much to shift the offer curve to the left-hand side. Okay? Or you can raise your offer price. That is called economic withholding. You just sell at a higher price. Okay? And the purpose is to increase the market price. So all of these things are called exercising market power. So the example is if a firm sells 10 units, suppose that the market price is $15. There are two ways of exercising market power. Option 1, offer to sell only 9 units and hope that the price, so withholding of your capacity, and hope that the price rises enough to compensate for the loss of the volume. So you only sell 9 units, you can sell 1 more unit, but you are hoping that because I reduced my supplying volume, that may increase the price, so I can sell the 10th unit at a higher price. Okay. And another option is offer to sell the 10th unit for a price higher than $15 and hope that this will increase the price. Yeah. And the profit increases if price rises sufficiently to compensate for possible decrease in volume. So anyway, when the price goes up, the demand may reduce. So, so revenue minus cost is the profit. But so you need to be careful about that. And so, as I told you, the price spikes can happen because of reduced supply. So this is a normal offer curve, but if you reduce your supply, it changes that, so price goes from here to there. So small reductions in supply cause large changes in peak prices. And that can happen, especially when the market equilibrium is in this region, not in this region. If we are here, the price does not change much, right? As you see. So when is market power more likely? Imperfect correlation with market share. Demand does not have a high price elasticity, and supply does not have high price elasticity. So imperfect competition, market power can happen, and demand does not have high price elasticity. Demand is almost fixed. Then if the demand is fixed, when we change the supply curve, we can exercise market power. Supply does not have a high price elasticity. Supply does not have a high price elasticity. That means, what does that mean? That means, this versus that, which one implies high price elasticity? So this is low price elasticity of supply, because even if price changes much, the volume cannot change much. That's the definition of price elasticity of supply. So again, this reason, it is easier to exercise market power when supplier has low price elasticity. So that's the meaning of that. Supply does not have a high price elasticity. And elasticity markets are more vulnerable than others to exercise market power. So that's why we need to have a regulator, an independent system operator in electricity market. Okay. And so the next goal is to how can we mitigate, reduce exercising market power. One way is to increase elasticity of demand and supply. Okay. Agree? And increase the number of competitors. So that's why we are going from vertical model to competitive models. And then, yeah, so increasing the elasticity reduces price spikes and the generator's ability to exercise market power. And then, why is that? Yeah, increasing elasticity means that, this slope, is it like that? Increasing elasticity means that, this slope is not that stiff, right? So that's like that. So when price changes, the consumers can reduce. When price goes up, the consumers can reduce their load. And then in this figure, well, what can we say? So, or we can say if the demand is elastic, then we can shift. It's not quite easy to explain, but okay. So this is a collection of all the demands given price. And if the demand is elastic, you can think this curve can shift it like that. Well, this explanation is not quite accurate, but yeah, if we can shift this curve to that, and then this region is less vulnerable to exercising market power compared to that. Okay. So increasing the elasticity of the demand is good, but there are several obstacles. The first one is actually we are using fixed price. As a residential customers, you are using fixed price. So you do not have much incentive to reduce your load as price changes. Okay. You only feel the need during a very hot summer day. Okay. And also to do that, we need to have efficient high-speed communication using smart meter. And also we need to have storage, either heat or battery, etc. Here, this storage means heat, intermediate products, dirty clause. Dirty clause means that you need to shift your using of laundry machine to another time slots. And not everybody needs to respond to price signals to get substantial benefits. This is interesting. So, if there are a very price sensitive customers, then they can reduce their load. Then the total load can be reduced, so the price can change. So not everybody need to respond to the price signal. And increased elasticity reduces the average price, as you know, but that's not the best interest of generating companies. Yeah. Okay. Further comments on market power. All firms benefit from the exercise of market power by one participant. That means, if there are only a few producers and one guy exercises market power, then the price goes up, then all the producers can have benefit. Okay. And unilaterally reducing output or increasing offer price to increase profits is legal. Unilaterally means, I just behave strategically solely myself. I can offer small amount of capacity, or I can raise the offering price as a producer. Okay, but yeah, so that is called unilaterally. I do not talk to other producers, but what prohibited is collusion between the firms. If they discuss and hey, let's reduce the generation to increase the price, that is called collusion, and that is illegal. And market power interferes with the efficient dispatch of generating resources. So from optimality perspective or social welfare maximization perspective, if somebody exercises market power that distorted the market, increase the price, so that's not good for social welfare perspective. And that means cheaper generation is replaced by more expensive generations. Who exercises market power? Okay, that's it. Any questions?
혹시
갑자기 왜? Okay, yeah.
마켓 파워를 이제 줄이기 위해서는 일래스티시티를 인크리싱 해야 되는 것 중에 옵션이 하나인데 디맨드 리스폰스가 그거를 또 하는 이유가 있나요? 연결되어 있는 건가요?
Yeah, demand response is one way of reducing market power, reducing the capability of exercising market power. Yeah.
첫 번째 줄에 한 명이 마켓 파워를 행사하면은 다른 회사도 이익을 본다 했는데 그게 어떻게 해서 이익이
So suppose that there are only 3 players in the market and you have a very high portion of the market. So you reduce your output, the quantity, and because then the price goes up, then these other guys can enjoy. Yeah, prices goes up, so I can increase my revenue. Yeah.
그 83쪽에서요. 거기서 얘기하는 베네핏이 뭔지 잘 모르겠어요.
Benefit. Your question is what it says is increasing demand elasticity is good for reducing the market power. And by reducing the market power, we can prevent the price is unnecessarily goes up. So that's good for consumers.
그러면은 여기서의 베네핏은 고객들의 베네핏인가요?
Yep. So exercising market power is from the producer's perspective. Okay, so they want to exercise market power to increase their revenue profit at the sacrifice of consumers. Okay. Any other questions? So because you did your homework, now you are curious about what's going on, which is a good sign, I guess. And you will have a subsequent homeworks in chapter 5 as well. Okay, let's go to chapter 5 then. Actually, in the first edition, it was in chapter 6, and ancillary service was discussed first, but no, the order has changed. So we first discussed the effect of transmission network on electricity. Why is it so hard to pronounce electricity? on electricity markets, and then we will discuss power system operation and optimal power flow stuff. Okay. So far we assume that all the generators and all the loads are connected in the same bus. In the same bus means there is no resistance and no capacity limits. So it's very, generators and consumers can meet freely in the same bus without worrying about the physical constraints. But now we need to think about the transmission network and the capacity limit of transmission line and the congestion in the transmission line, and also the power losses because of the ohmic losses. Okay, and we will discuss two forms of trading. We first discuss bilateral or decentralized trading, and then I'll go to pool or centralized trading. Okay, bilateral trading means the transactions involve only buyer and seller as before, but here we have transmission network, but the transmission network operator or system operator should not get involved in the trading directly. So the job of system operator is just let this seller and buyer meet and transact power energy using this physical facility, and just check whether this kind of transaction can happen or not, considering physical constraints, maximum power flow limit, conditions, power losses, etc. Okay, so in this kind of bilateral trading, because transaction only happens between buyer and seller, any kind of transaction would be okay in terms of price and quantity and all the conditions. So as long as this seller and this buyer are happy with the transaction, the system operator doesn't care. That means the price can be very high. I don't know why, but the price can be very high or can be very low. This is just a matter of these two, buyer and seller. Okay? And the system operator just make sure that this transaction, if they agree to transact using the condition, the system operator only needs to make sure that this transaction can happen physically. Okay? So, maintain balance and security of the system. By the way, again, this security does not mean the information, the communication security. Think about power system was invented first, and then communication, analog communication or digital communication were invented later. So you are using internet all the time, every day, so you are thinking of information security, communication security, but power system exists before the communication system. So the secure means the balance, reliability of the system. Okay. So SO, system operator, need to maintain the balance and security of the system. So if the transaction is not possible, then that should be limited. And so limits the amount of power that generator can inject at some nodes or bus, if security cannot be ensured by other means. Okay. So that means as long as the system can support that transaction, that transaction need to happen. By the way, node, bus, same terminology. So let's look at one example of bilateral trading. We have two bus A and bus B. This bus is just a metal, okay, a huge metal, where these generators are connected or the load is connected. So in this example, generator 1 sells 300 megawatt to load 1. Generator 2 sold 200 megawatt to load 2. Prices are a private matter. It needs not be revealed to the system operator. Again, I don't care. Yeah, this guy wants to transact power 300 megawatt from here to there, and this guy wants to transact 200 megawatt power from here to there, and the system operator only check whether they can be supportable or not. Okay. So the price are a private manner, but the quantity must be reported to the system operator so that it can check the security, power security. By the way, I think this is the first diagram using this kind of symbol in this class. So yeah, we have a bus. Again, this is just a huge metal plate. And this is a generator, and this is a symbol for load. And we are using this kind of diagram. So the bus A is connected to bus B like that. This is called a single line diagram, which you are not familiar with because you didn't take power system course before. So this is equal to some load. You are familiar with this kind of diagram, plus, minus. AC, this is a load. Let's just ignore the transmission line losses. So this is a load. Sometimes we have this kind of capacitance or some reactance component in the load, especially if your load is like air conditioner or washing machine. It has a motor, then obviously that has the coil component. If your load is just heater or light, then you have only this kind of resistors component. Anyway, so you are familiar with that. But this is simply drawn in power system like that, using single line. Okay. Actually, even though we didn't talk about that, it assumes balanced three-phase system. This is a single phase system. Three-phase system means it has three lines. It has three lines again, three lines and collected. Another that, and you can see that when you walk through the streets. When you look at the transformer and another transformer, count the number of lines. That is 3n plus 1. This plus 1 is called neutral line. Okay, so theoretically, we are assuming balanced three-phase, but in practice, it's slightly not balanced. So that unbalance can be compensated using a neutral line. So when you go to the highway or when you walk through this street, just count the number of lines. That is 3n plus 1. Or sometimes you can be confused because using the same pole, the electric line and also the communication line are installed together. So yeah, don't be confused. Anyway, yeah, so this is called a single line diagram. So corridor, this is corridor. If capacity of corridor is more than 500 megawatt, we have no problem. But if capacity of corridor is less than 500 megawatt, then some of this transaction need to be curtailed. Okay, and that means when congestion happens, we have transmission network. Sometimes congestion happens. So when congestion happens, who can transact first? Who can use this line first? We have that kind of issues. So that means there is a concept of transmission right. Okay, transmission right. In Korean, that is called 송전권. Okay, so which transaction should be curtailed? So yeah, important question and interesting question. But again, in this bilateral transaction, the system operators doesn't care about the price. So in this case, we just use administrative procedures, which is not economically efficient. Okay, which is not economically efficient. So system operator could use administrative procedures, something like whether this transaction is firm transactions or non-firm transactions, or the order in which they were registered, or other historical considerations. So it does not consider relative economic benefits and economic efficiency. And so better to let the participants themselves decide what makes sense or not. So anyway, yeah. So what I want to tell you is that participants now need to purchase right to use the network when arranging a trade in energy. Okay, so that is called the physical transmission right. Again, 송전권. and yeah, so this physical transmission right is also kind of good. So it can be traded. If you have transmission line right, you can sell it to someone else. Okay, but that's not our main topic. So here, let's see how much are these producers willing to pay. Yeah, now this is the price. Actually, this is not given to the system operator, but no, just for discussion. Suppose that we know that. Okay. Yeah, this is transaction, $30 per megawatt hour. Another transaction, $32 per megawatt hour. And this generator actually sells nothing, but their marginal cost is suppose that is $35 per megawatt hour. Then how much would L1 and L2 be willing to pay for transmission rights? Obviously, generator 1 can pay up to $5 to compete with that guy. Okay, so cost plus transmission right expenditure should be less than that competitor. So, and L2 should not pay more than $3. L1 should not pay more than $5 for transmission rights. So there is a market for trading of this transmission right, which is not our topic. And let's think about what kind of problems we have with these physical rights. In terms of two factors, the parallel path and market power. So in this example, we only have a single path, single corridor, but power system is a network. So when there is a seller and buyer, there can be multiple paths, right? So that affects transmission rights. And also because of this congestion, when congestion happens, we will see that when congestion happens, it is easier to exercise market power. Okay. So let's see the effect of parallel path first. Just for simplicity here, we assume there are only two paths, and this is the impedance of line XA and XB, and the power flows from here to there. And then using Kirchhoff current law and Kirchhoff voltage law, KC and KVL, we can easily compute that the voltage is something, and then current flows inversely proportional to the impedance. So the power is voltage times current, and voltage is same for this path and that path, right? So the power flows inversely proportional to the line impedance, right? So if the injecting power is P, then the power flow on line A is that, inversely proportional to the impedance. XA and XB, so XA plus XB. XB over XA plus XB is that, right? And XA over XA plus XB. Obvious thing. So, yeah, it happens when we have two paths, but in power network, typical example is about 3 buses. So you will see a lot this kind of examples in your textbook from today. We have 3 buses: bus A, bus 1, bus 2, bus 3. And each bus has generators or loads, or both of them, or sometimes have multiple generators. Okay? So yeah, we have branch. This is called branch. And each branch has its reactance component per unit. So this is a normalized value. And for simplicity, we ignore the resistance component in the line. The line only has reactance component. So there is no, And the capacity of the line is that. Magic. So yeah, we have bus 1, bus 2, bus 3, and they are connected like this. And this is the symbol of generator, and this is the symbol of load. Y, D, another load, Z, generator A, generator B, and generator C, and another load. This is bus 1, bus 2, bus 3. Okay. Yeah. And the capacity of branch 1, 2 is 126 megawatt. And 1, 3 is 250 megawatt. And 130 megawatt. And the reactance to 3, this is a point 2. Okay. And suppose that we are talking about bilateral transaction in 3-bus system. So suppose that there is a transaction 400 megawatt between B generator and load Y, and they need to buy transmission rights on all lines, either this path or over that path. So actually, 400 megawatt power is injected from here, but some of them flows on this line and some of them flows on that line, depending on the impedance. So yeah, that is determined from physical law. Actually, that's not a difficult error at all. So F1 is this power flow, and again, this is just metal. Okay, so when you compute the power flow, that and that, you don't need to care about these things. Okay, so the impedance, this line is 0.3, and this is 0.2. So yeah, 0.3, 0.2. So 40% of power flows on line 1. So yeah, 40%, right? So yeah, 160 megawatt. And 60% power flows on line 1-3. That is here. Right? Right? Yeah. So yeah, this is 160 megawatt. And this is 240 megawatt. Okay. But let's see what happens. What happens? This is not possible because the maximum capacity is 126 megawatt. And no, this is even greater than that one. Okay. So the system cannot support this bilateral transaction. But if there is another counterflow, that can be possible. And suppose that there is another bilateral transaction from D to Z, 200 megawatt. Okay, so 200. 200 is injected from here, and that need to go to there, either this path or either using that path. So again, so impedance 0.3 or 0.2, so 40% goes that way and 60% go that way. So yeah, 40%, 8 megawatt, 80 megawatt counterflow, and 120 megawatt logically. So from a physical point of view, yeah, physically the net power flow from here to here is just 80 megawatt, right? And from here to here, 120 megawatt, and this system can support that. Okay. So the resultant flows are within the limits. Physical rights and parallel path. So counterflow can create additional physical transmission rights. Yeah, that's an interesting part. And economic efficiency requires that these rights be considered. But this is decentralized trading, and system operator only checks overall feasibility. Okay, and the participants can buy or sell the transmission line, transmission right bilaterally. Okay, as I told you, this is a right, this is kind of a good, so they can be exchanged together bilaterally. So in theory, if there are enough participants, the market can discover the optimal point. But in practice, that's complex. Complexity and amount of information involved are such that it is unlikely that this optimum can be found in time. So anyway, so what I want to tell you is that this kind of, so when we think about bilateral transaction, we have an issue of congestion and issue of transmission right. Okay, and then, yeah. And also, these physical rights and market power are related. And the reason is because, yeah, G3 only generates at bus B, and G3 purchased transmission right from A to B. Yeah. Suppose that, yeah, G3 has the transmission right on this line. That means, this. Yeah, 3-bus system, we are back to 2-bus system, and yeah, it has some limit, and these guys have some transmission right, purchased that transmission right, but didn't want to use that, because if that guy didn't use that anyway, this physical the system operator thinks this capacity is reduced. So that means that also can reduce the power transaction from here to there, right? So G3 does not use the transmission right or resell these rights, but what G3 wants to do is to make profit. So, okay, what I want to say. What I want to say is when this guy has the transmission right, but if it does not use that, then that's not good from society perspective. Okay, so so G3 can exploit its transmission right to increase the price at bus B. The reason is because, do you see what I'm saying? Maybe not. So we have a capacity here. Okay, so sometimes congestion can happen. So we have a concept of transmission right. And suppose that this generator 3 purchased the transmission right. Okay, then he reserved his own capacity on this line. That means, for these guys, the maximum capacity is actually reduced. The maximum capacity they can transact from here to there is reduced, right? So anyway, so this kind of exercising market power and the price at node B can increase. Think about it. Okay, I don't need to explain all the steps. Okay, because that may make you more confused. Just read the textbook. So anyway, what I want to tell you is that because this guy can exercise market power by not using its transmission right, the regulator need to prevent that. So that is called use them or lose them. So you cannot withhold your transmission right when you do not transmit. Yeji, are you okay? Kind of. Okay. So from regulator's perspective, use them or lose them. Lose them is okay, but in theory, it's not easy to implement. Think about it. Okay, so far we talked about bilateral transaction. Questions? Questions? So far so good. Very easy example. 2 bus or 3 bus for bilateral transaction. Okay. The transaction is just up to the seller and buyer. System operator only needs to care about the transaction can happen. Only need to make sure that the transaction happen. But let's think about another types of trading, the centralized or pool trading. And this is better than bilateral trading in terms of achieving the efficiency, economic efficiency. So producers and consumers submit bids and offers to a central market, as you see. So we have the supply curve and demand curve. And at the intersection point, the market clearing price is determined. And the independent system operator, ISO, selects the winning bids and offers in a way that optimally clears the market and also need to respect security constraint imposed by the network. And if there is no congestion and no losses, then the price is same over all the network. That's the ideal case. But in reality, no, congestion can happen, and also there are power losses. So the price can be different depending on the buses. So far we talked about this one, SMP. You remember what it is? System marginal price. Okay? But if the network is big, then there can be congestion on some line. So no longer we have a single SMP. So that's why we have another concept in which the price depends on the location, the bus, where the generator or load is connected. So that is called locational marginal pricing, LMP. Okay, so when congestion happens in the network, you see that the price can be different from bus to bus. Okay? And to explain that, this textbook, again, uses these two imaginary countries, Bulgaria and Moldavia. Yeah. So in this example, in your textbook, please read the textbook. Anyway, you will read the textbook to do your homework. Anyway, yeah, we have two countries, and this country has this amount of demand, 500 megawatt. This country has that amount of demand, 1500 megawatt. For simplicity, let's just assume that Bulgaria market is perfectly competitive. Yeah, perfectly competitive. And again, yeah, this is also perfectly competitive. Yeah, and no congestion or no losses within each country. So Bill, who is a system engineer, is now about to analyze what happens when we connect these two countries by installing a transmission network. Okay. So yeah, but for each country, no congestion and no losses. So single price for electrical energy for each country. And here, because this is a perfectly competitive market, the price is equal to the marginal cost of the generator. Yeah. So yeah, the guy, the system engineer, obtained this curve. This is the price, this is quantity. What is it? Supply curve of Bulgaria and supply curve of Moldavia. Okay, so actually this is same to the marginal cost curve, right? So fixed cost plus the slope. Another fixed cost in the slope. This slope is higher than that. Anyway, so under this situation, they are not connected yet. The total load is 500 megawatt. This is perfectly competitive market. And then when the demand is that much, the supply is that much. So the marginal cost at the time is $15, and that's the market clearing price. Here, the demand is 1500, and using this curve, the SMP is $43 per megawatt hour. Then what do you want to do now? You are a system engineer. You are a power system consultant. You are seeing these two markets, Bulgaria and Moldavia. What do you want to do? Energy is much cheaper here, right? So when they are connected, these guys may want to sell energy to them, right? Trade between two countries. So yeah, they are now connected. Then we are curious about the economic effects of this interconnection. by the way, this connection means we have transmission lines. The transmission tower, when you see when you go through the highway, okay? Yeah. So when you read the textbook, the author says, they were not quite friendly each other, but now peace has come. They want to exchange goods, also energy. So yeah, this kind of thing can happen. Anyway, so here for simplicity, we do not impose the maximum generation capacity. Okay. So because this is a cheaper generator, they want to generate 2,000 megawatt, and this generates 0 megawatt. But you think this is cheaper than that. Actually, that is true. And this marginal cost curve is always lower than that. That minus that is always positive. So interesting. Anyway, so if these guys produce all the demands, then that gives us this marginal cost for Boldria and Sildavia. Okay, $30 and $13. So this is not what we expected. Okay, so this is not a market. This cannot be a market equilibrium. And okay, what we are expecting is that at the market equilibrium, this is connected by a line, and then if the market is effective, these two markets are effective and they are connected, then what happens is we need to converge to some market equilibrium. So our next job is to determine what is the market clearing price. This is not the solution. This is not the solution of interconnecting these two countries. We can find a better point where everybody becomes happy. Okay? So, yeah, what I'm saying is, so intuitively you see that if all the power is generated here and nothing is generated here, then something is wrong. Okay, actually this price is too much, so we can find a lower price than that. Okay, so at the market equilibrium, the price here and there should be same when there is no congestion here. Okay, so the market clearing price, pi b, pi s, at two different countries should be same. And the total supply should be equal to total demand. The total demand here is 2,000 megawatt. Okay, and then how can we solve it? Actually, you need to use this marginal cost curve, this one and that one. So the way of solving it is to can you think about that? How to solve that? What is the market clearing price? Are you agree with this condition? If the market clearing price are different between two countries and they are connected and there is no congestion and no power losses, then that is just adjusted again by someone who wants to take the advantage of that. If something is more expensive here than that, then they can buy energy from here and sell it to there. Right? So anyway, the price changes, but it converges to a same point. That's the market clearing price, right? So the way of solving it is just simply that at the equilibrium, they are same. So the generation capacity can be expressed as a function of price. Same thing here. So PS is a function of pi. PB is a function of pi. And PS plus PB is that. And we have just single variable, right? So the market clearing price can be computed, and that's this one. $24. And using that, the generation amount is 1,433 megawatt. Blah, blah. And the sum of these two is 2,000 megawatt. And yeah. And yeah, so this much is generated here, and this is internal load. So that minus that is 933 megawatt flows from here to there. That is same to the total demand 1,500 minus the generation. That much is that. Okay. And graphically, it looks complicated, but this is a cute figure. So, okay, this is the amount of generated power, and this is the price, but we have two axes. The pi b of country Bulgaria, and pi c country for Sylvania. And actually, we are looking at this kind of graph, but yeah, that is true. But here, this is just flipped. Okay, so from here to there. Okay, so that's why we have this supply curve and that supply curve. Okay, so because the demand of two countries is 2,000, this is 2,000. So when you draw a figure like that, at any point, at any price, country B generates that much, country S generates that much, and the sum of them is not 2,000. Yeah. When you fix this, actually the intersection is just the solution. Okay. So yeah, PB and PS. And this is the local demand of B, local demand of S. So the generation minus local demand is the power flow from Bulgaria to Sylvania. Okay. Good. Any questions about this figure? Minjae? Okay. Then let's think about what was our assumption. Our assumption is that this line capacity is enough. But next step would be the line has transmission limit. Okay? So next topic is constraint transmission. What if the interconnection can carry only 400 megawatt? So yeah, that means this is the internal load, and this is the maximum line capacity. So this guy can generate only at most 900 megawatt. And Sildavia internal load minus 400. What is that? Yeah. So anyway, 2,000, and this much is generated. So the rest of should be generated at Sildavia. So using this volume 900 and 1100, the marginal cost of B and S is 19 and 35. So yeah, in this simple example, because we have the transmission capacity limit, the price at B and S are different, $19 and $35. So price difference between The prices are different between these two locations. So that is called, this is called, and that is called locational marginal pricing, LMP. And yeah, LMP or nodal pricing, they are used interchangeably. Because the bus, node, the same terminology. But in Korea, we do not have LMP yet. Even if we have congestions on the transmission line, for some transmission lines. So this is another graphical representation such that, what is it? So, yeah, under this circumstance, the country B can generate only this much. So this is the LMP of Bolduria. This is the LMP of the Sildavia. So this is the summary, interesting summary. Actually a homework problem for you by next Monday. We have only a few minutes, so I will finish here. But so this is the summary sheet. When these two countries are separated, amount of power, the price, the total demand, the expenditure of the customers. So this revenue is this times that. Sildavia, total power, price, revenue and expenditure, that. So total revenue and total expenditure are same. And when they are connected, we connected by an infinite line, then two perfectly competitive markets are connected by an infinite capacity, then this is just a single competitive market. And then these numbers are from here. Okay, so check it on your own. And when there is a congestion, again, this value, that value, using that value, you can compute all of this. So check it on your own. Check it on your own. And there is one interesting fact here. Check it, but they are different. They are same, but they are different. So total expenditure from customers and the total revenue for generators are different. It turns out that they are different. Actually, yeah, check it, and then you will see it happens. And think about why is that. So your homework by next Monday is to check this table, check this is correct, and think about why that happens. Of course, that happens because of the congestion in the transmission line. Okay. Any questions? Okay, I will see you next Monday. Thank you.